The objective of this lab was to determine the effects of air resistance and drag. So to do this, two objects were analyzed. First one was a tennis ball. The motion is analyzed from after the ball is dropped from the hand to the instant when it hits the floor. And a calibration stick was used that shows that the tennis ball is 6.7 times 10 to the negative 2 meters long. The axes are oriented so that the ball falls in the negative y direction. When this was analyzed in Python, the ball's mass was plugged in first as 0.00567, and the drag force was found to be 0.0075. The way that this was calculated was by plotting the points of the actual data and comparing it to the experimental data when plotted. So, as you can see here, the data matches closely, although it's not perfect, most likely because the motion of the ball wasn't exactly marked perfectly in the tracker video. So the constant of proportionality was found to be 0.0075, and the force of the drag is equal to the constant of proportionality times ball's velocity, but is also in the opposite direction of motion, so it is negative. That means that the overall net force acting upon the object is the force of the gravity plus the force of drag, and the object's motion ends up looking like this, like the green marker shown on the graph. The next object analyzed was a cotton ball. The falling cotton ball the motion was also analyzed after it was dropped from the hand to the instant when it hit the floor. And in this, the axis is also oriented in the same direction, in the negative y direction. This was also modeled in Python, and it was found that the mass of the ball was 0.0002, and that the drag force was equal to 0.01. And again, the force of the drag is equal to the same thing it was as with the tennis ball, and so is the overall net force. So this was also determined by observing how close the graphs were of the actual data and the experimental data. So as you can see here, they were very close, which means that the constant of proportionality is accurate for this model. So why is the constant of proportionality bigger for the cotton ball? It's bigger for the cotton ball because the force of drag is higher. Because the cotton ball has more air resistance, the force of air resistance affects its speed more, which means that it has a higher constant of proportionality. Okay, now what if what if there was no drag? How would this experiment look? Here I graphed what the motion would look like if there was drag, that is the red data points, and the blue data points model the data if there was no air resistance. This shows that there's that air resistance has a big effect on the motion of the cotton ball. If the object was thrown downward initially, then the object's acceleration would be higher, or velocity would be higher, which means that drag would have less effect because drag would be equal to the ball's the proportionality constant times the velocity.